welcome to the Data Science Decoded podcast. Happy to be back with a super cool paper today. I'm here with Liron and Mike. How are you guys?
I'm good.
Not bad, no complaints. And it's gonna be a cool episode because this paper is rather short. And although it is short, it is very famous and seminal paper of Jeffrey Hinton. Jeffrey E. Hinton.
And Rumelhard and Williams.
By the way, Rumelhard, it's I'm not sure, but it sounds quite familiar. Have we discussed one of his papers?
No.
I'm wrong. Okay.
No. How are you, Liron?
I'm good. I like the paper. It's like very basic. Everyone knows it, but we're looking at the publication, like where it came from. And what could they see back then? It's always interesting to see.
Yeah, so to our listeners, it's a paper that was published at Nature, titled Learning Representations by Back-Propagation Errors, in 1985 by David E. Rumelhard, Geoffrey E. Hinton, and Roland J. Williams. And today we call it the deep learning paper. So it was the influential paper that introduced the ideas that we all know today. So yeah, it's because it's Nature, it's short. They don't have a lot of space to write things. So the episode today, I would call it Netflix and Chill. We're gonna do it in a chill way, discuss, maybe also talk about the way we were introduced to the concepts and what we think about them today, as there's not a lot of math to cover. And what else? So we're all familiar with Hinton. He won last year, 2024, the Nobel Prize in Physics due to his contributions to deep learning and the foundations of deep learning. We won't go into discussions why it's physics, maybe in a different episode and what we think about that. But also he won the Turing Award. I think it was 2018 or something, or 19. And yeah, so he's famous. We're all familiar with him. And there's Rumelhard and Williams. They are both cognitive scientists. So their work was mainly around neuroscience. And as far as I did research, Hinton said that Rumelhard did a lot of the work behind the ideas. That's why he's the first author to this paper.
Also worth noting that the journal is Letters to Nature. So it's kind of like Nature, but it's not the Nature publication. Right. It's a shorter form. This is basically a note.
Yeah, it's like 3 pages with some photos, and
so it should have been called a seminal note and not seminal paper. Seminal letter.
A note is a paper.
Yeah.
Technically.
Okay.
Cool. I'll read the abstract and then we can discuss the important parts. So he says, we describe a new learning procedure, back-propagation, for networks of neuron-like units. The procedure repeatedly adjusts the weights of the connections in the network so as to minimize a measure of the difference between the actual output vector of the net and the desired output vector. As a result of the weight adjustments, internal hidden units, which are not part of the input or output, come to represent important features of the task domain. And the regularities in the task are captured by the interactions of these units. The ability to create useful new features distinguishes backpropagation from earlier, simpler methods, such as the perceptron-convergence procedure. And besides one, it is the Rosenblatt paper on the perceptron we reviewed, 20 episodes back.
Yeah,
so what are your thoughts on the abstract? Yeah,
actually, this abstract is a quite cool definition of deep learning and its difference from one layer perceptron. So for me, it is cool to read it, to read it back to 1986, because I'm not sure. I'm not sure Hinton was the first who used the term neuron-like units to denote stuff within deep neural nets, but I think at least I see it for the first time. I don't remember the papers we discussed were using this neuron term. Am I wrong about it?
I think I heard an old lecture by Hinton where he says he was the first to use the term.
Okay.
But we had the last episode of the verbose PhD on which he had back propagation. He also discussed neurons, right? He had there also this concept.
Yeah, I don't
really?
think he used neural networks, and there was another model of neurons that was common. It was like a mathematical model of biological neurons, and it felt like he meant that more
Yeah.
than he meant these kind of neurons.
Yeah, he wasn't talking about the things we're going to discuss here. In a sense, like the mathematical formulation was different for sure. But I just said he did mention that the networks he was talking about could be also like neuron-like. But he didn't say neural network.
Yeah, it was a question then, right? Can you simulate a neuron? So I think there's a seminal paper from the 70s that had a pretty good model of a single neuron. Of course, you cannot simulate the whole brain like that. That's like a lot. And it's not a perfect model either, but it is a model of a neuron. So yeah, that's something that used to bother researchers. How do you simulate one nerve cell?
Okay, I'll continue reading. So the introduction is relevant. There have been many attempts to design self-organizing neural networks. The aim is to find a powerful synaptic modification rule that will allow an arbitrary connected neural network to develop an internal structure that is appropriate for a particular task domain. The task is specified by giving a desired state vector of the output unit for each state vector of the input units. If the input units are directly connected to the output units, it's relatively easy to find learning rules that iteratively adjust the relative strengths of the connection so as it progressively reduces the difference between the actual and desired output vector. So if there's no hidden layer, right? And so he says it's easy to learn, and he cites a paper. But then he says learning becomes more interesting, but more difficult when we introduce hidden units whose actual or desired states are not specified by the task. He says,
by the way, Daniel, as for the term of self-organizing networks, I'm not sure, but it seems that today this term is used to denote different concepts, something with adaptive computation or self-training. I'm not sure that a classic neural network can be called today self-organizing network.
Yeah, he probably meant from like a neuroscience perspective, like they use this word probably because again the two other co-authors come from neuroscience and cognitive science.
Okay.
He continues, or they continue, the learning procedure must decide under what circumstances the hidden units should be active in order to help achieve the desired input-output behavior. This amounts to deciding what these units should represent. We demonstrate that a general purpose and relatively simple procedure is powerful enough to construct appropriate internal representations. That sounds fun.
That's actually interesting, right? Because that's where he's talking about nonlinear learning.
Yep. He continues, or they, again, the simplest form of the learning procedure is for layered networks, which have a layer of input units at the bottom, any number of intermediate layers, and a layer of output units at the top. connections within a layer or from higher to lower layers are forbidden. So there's no like skipping, right? You always connected
No,
to the next layer.
he's
No?
actually allowing skipping. He's discussing that explicitly.
But connection can skip intermediate layers.
So you cannot go from the advanced layers, from the higher layers, back to the lower layers. You cannot
So
have
it's not like it's not an RNN.
it's well, he's not talking about through time, but there's no algebraic loops. So if I have x equals y plus half x, that's an algebraic loop, right? You have to move x back. And he's avoiding those. It says there's not going to be anything like coming back from layer 4 back to layer 1.
Okay.
Okay, but Leron, that the connection from layer 2 to say layer 5,
That's
is
okay.
it allowed here?
Yes.
Okay.
So forward allowed, that's what you mean?
Yes.
Yeah. Any forward is allowed.
Yes.
Okay, cool. Thank you for that. An input vector is represented or is presented to the network by setting the states of the input units. Then the states of the units in each layer are determined by applied equations 1 and 2 that we'll cover soon to the connections coming from the lower levels. All units within a layer have their states set in parallel, but different layers have their states set up sequentially, starting at the bottom layers and working upwards until the states of the output units are determined. So it's like a forward pass is starting from the input here at the bottom, and then sequentially you move between layers. But at each layer, everything happens in parallel. Cool. And then now we're going to see the equations. The total input xj to unit j is a linear function of the outputs yi, of the units that are connected to j, and of the weights wji. And on those connections, and this is equation 1. So it says xj is equal to the sum over oi's of yi times the weight wji. So in a sense, it's a linear combination of the weights times this yi, which is equation 2, and yi or yj is defined as the nonlinear function. And in this case, this is like a hyperbolic. What's the name of the function? No, this is the we talked about it.
That's the sigmoid.
Sigmoid. Yeah.
Yeah. So
we talked.
You went very far to hyperbolic.
Yeah, I thought. I thought about that. Yeah.
It's practically a tan h, just shifted and scaled. So it is an hyperbolic function in a sense. But this is, I think, not the most standard form of a sigmoid, right? You usually have exponent of x over 1 plus exponent of x, which is the same, right? But maybe the viewers are not used to that form.
You know, it is 1996, so it just takes smaller number of letters, you know, to write it down.
Well,
so maybe this is probably a reason.
Or they just like the formulation, right? It doesn't actually matter. But
maybe.
I mean, if they would have wanted to minimize number of letters, they would have used the matrix form, which is very common now. But they are writing the matrix multiplication explicitly in equation 1.
Okay, I see your point.
Okay, to our listeners, figure 1 is they drew a neural network, which is an interesting drawing because like the input is like in the middle. This line is the inputs, and then there's the hidden layer on the side, and then the output is on top. I don't know why, but that's how they drew it. Just to illustrate, we won't go over the exact example they talk about. But they continue with the explanation. They say it is not necessary to use exactly the function given in equations 1 and 2. Any input-output function which has a bounded derivative will do. That's interesting. However, the use of a linear function for combining the inputs to a unit before applying the nonlinearity greatly simplifies the learning procedure.
And I think, guys, this is one of the most important, maybe even the most important sentence of this paper, because this linear function and the nonlinearity invoked on it, actually, we can define that backpropagation exists basically because of this. Okay, and all the deep neural nets, as we know them today, nowadays, exist because of that, because of this formulation, because it's linear and non-linear invoked on it. Okay, so for me, it is a core of this paper.
More than that, actually. So if you think about convolutions that are very common and important now, right, they would come like over a decade later. But convolutions is just deciding where you don't have weights, because you can look at an image as a vector, right, which is just, has more components. A tensor is a vector in memory, actually. And then you just decide which connections you have and which you don't. And that's the same as having convolutions. Like convolutions are a special case of choosing the connections. So,
but I think the paper of LeCun is 89. The first CNN paper.
I remember it as 98. Maybe I'm wrong.
No, I think it's 89. You can check it now.
It's a very famous video of 93 when he was showing.
In real time how it works.
Yeah,
on the
in
computer.
real time how he detects digits or something like that.
Yeah,
digits. Very old monitor,
Okay, so let's continue. Now it's an important topic. It says the aim is to find a set of weights that ensure that for each input vector, the output vector produced by the network is the same as or sufficiently close to the desired output vector. If there is a fixed finite set of input-output cases, so let's call it your training set, the total error in the performance of the network with a particular set of weights can be computed by comparing the actual and desired output vectors for every case, and then summing it, and you get the total error E. And it is defined as, this is equation number 3, as the double sum over C and J over open brackets YJC minus DJC squared. D is your desired outcome. Let's go with the label that we have in our training set, right? So in the sense is calculating the mean square error, right?
Yeah, that's exactly what it is.
Okay. What did you say?
I said that's exactly what it is. That's the mean square error with one sum over the components of the vector and the other sum over the examples.
Mm-hmm.
Yeah. And we call it the loss function. This is a particular case of a loss function.
Yep. Yeah, and to me, when I see always loss functions, I'm thinking, wait, what about maximum likelihood? Wait, what about KL divergence? How did they came up with this metric? And by the way, this case that they're showing is true when the error has normal distribution.
Mm-hmm. It's right? The maximum likelihood.
Under, so they have an assumption here. This is like a regression problem with assumption on the noise. Which again, I like to go into those rabbit holes. They somehow assume this is the case without any background, but because it's a letter, probably that's the reason. Cool. Let's continue. And they say, we have already described the forward pass in which the units in each layer have their states determined by the inputs they perceive from units in the lower layer. So this is equation 1 and 2. The backward pass which propagates derivatives from the top layer back to the bottom one, is more complicated. And
So
he
it
says,
basically tells us that forward propagation is simpler than back propagation, which is kind of correct because it is in many cases it is simpler to compute function value for a given x than to compute all these derivatives and gradients with the chain rule. So this is basically that.
yeah, and that's exactly what's happening now. And they describe the back-propagation by using the chain rule. Again, I don't know if we want to describe all the equations. They should be familiar to anyone who ever done anything basic with neural networks. But the idea is to use the chain rule and back propagate the error from the output. So it's the dE to dy back propagated all the way to the weights. So then we can know, given a pair, so in a training set, we know the values, we know the desired outcome, we can back propagate the error to all the weights and then update them. So again, this is in high level what's happening in back propagation. Unless you have anything else to say here, guys. I want to add that this formulation of the chain rule that they're using is the same that we are taught today, right? Even similar terminology. We have W for the weights, and I think X and Y, like Y is the label, the outcome. It's similar notations.
Yes.
Yeah, but the only difference, as far as I remember, because remembering how back propagation is working in a very big with details, I don't think it is needed to. Any data scientist needs to understand it, in general. But still, today, in order to do it correctly for our multi-billions neural networks, when we compute forward propagation, we are saving the values for different layers in order to make it faster. I don't remember how exactly it works, but I'm pretty sure they are saving some values of the intermediate layers.
There's a lot of caching involved, but I'd say that's more software engineering than he cares about in 86.
Let's see, continues here. At the end, he derives how change in the outcome, in the error, propagates to the weight. And then he says, that's important, one way of using the delta E to delta W is to change the weights after every input-output case. This has the advantage that no separate memory is required for the derivatives. An alternative schema, which we used in the research reported here, is to accumulate the delta E to delta W over all the input-output cases before changing the weights. And then he says the simplest version of gradient descent is how to change the weights is to change by the amount proportional to the accumulated error. So the change in weights, delta W, is proportional to some epsilon with minus, because we want to penalize the weights in order to reduce the error, which is proportional to this error propagator. So this is gradient descent. Yeah.
By the way, in this paragraph, it contains two extreme cases of gradient descent. The first case is we used to call it stochastic gradient descent, and you perform gradient descent step after for each point. And the full case, you perform gradient descent for all the data. Today we are not doing not that and not that. We are doing a mini batch, so using a small part of our data set for weight update. Yeah.
But it's very interesting that he's actually doing that in mini batches of one and calculating them separately. So he's doing mini batch accumulation that we would start doing again much, much later already here.
Yeah.
Good point.
Interesting.
And then he talks about how to improve. He says this method does not converge as rapidly as methods which use the second derivatives. So we talked about in the last episode on the Haitian. All right, I said correctly. It's the second derivative, and to help you converge faster. But he says this first derivative is much simpler and can easily be implemented by local computation in parallel hardware. Then he continues to say it can significantly improve without sacrificing the simplicity and locality by using an acceleration method in which the current gradient is used to modify the velocity of the point in weight space instead of its position. So we call it
Master of momentum.
yeah, momentum, exactly.
It is, I actually, when I read this paper, I totally missed this paragraph. And this is momentum. It's interesting to compare it to the Nesterov momentum. And, I'm pretty sure Nesterov did something different. But guys, it looks like quite similar.
This is a momentum term.
Yeah, so, because he talks about speed. Right?
Okay.
He talks about velocity. Yeah, it's similar to momentum.
Okay.
But again, he doesn't cite. So maybe in 86 they had some concepts of optimization and how they do it faster, for sure. He probably didn't invent this idea. Then he says, to break symmetry, we start with small random weights. Variants on the learning procedure have been discovered independently by David Parker, Personal Communication, and Jan LeCun. So he did cite those two.
And
this is like the initialization, right? When he means to break symmetry.
Yeah. So if all the weights start from zero, then like two neurons in the same layer cannot have different weights, right? If they start the same, they always get the same gradient, and assuming they have the same connections, and they will always stay the same. So that's not what we want, right? We want different neurons to give us different parts of the representation. So in order for a difference to be feasible, he initializes them slightly differently. That's standard practice today. The framework does that for you. But it's a very important thing he's touching on here. That's like the very basic thing to make the networks able to actually learn.
And here he talks about how, in a sense, today you can learn the XOR function, which is asymmetrical. So he talks about it here, that you can learn also asymmetry. We won't go into this. Let's see what else.
By the way, Daniel, it's quite interesting. I think I claim here that this detection symmetry problem can be solved with the one-layer neural network. And actually,
he talks about it.
Two-layer neural network, right?
He says it, yeah. You need hidden. But look, I want to read the important part.
Okay.
The most obvious drawback of the learning procedure is that the error surface may contain local minima, so that gradient descent is not guaranteed to find a global minimum. However, experience with many tasks shows that the network very rarely gets stuck in poor local minima that are significantly worse than the global minimum. We have only encountered this undesirable behavior in networks that have just enough connections to perform the task. Adding a few more connections creates extra dimensions in weight space, and these dimensions provide paths around the barriers that create poor local minima in the lower dimensional subspaces.
That's actually alluding to the lottery ticket hypothesis. Like in all the things we came up with later to make convergence better. So there's one aspect that we know today that he absolutely nails here, and there's one that he's actually not talking about, which probably he didn't think of at the time.
What do you mean, which one?
So for a very long time, the literature discussed the problem of local minima, and are we likely to stay in a bad local minima, and is it because that good local minima are flatter than bad local minima, and so forth. And then somewhere around 10 years ago, I think, they reached the conclusion that local minimas are not actually a problem. The problem is saddle points, where we have very small gradients, but it's not a minima, right? There is a direction to improve from
Yeah.
there. It's just that we were stuck in small gradients. And I think that's what eventually led to all the methods of cyclic learning rates.
Yeah.
So, and he's not touching on that here, which is really tricky. I never thought of that, obviously. I just read about it. So, yeah, I mean, just worth noting.
And there is, guys, there is one more point here, and about local minima. Today we are talking about networks with billions or hundreds of billions, maybe trillions of parameters, and there are a lot of research on it. And this function, this big neural network, this function is crazily non-convex. And I saw claims that in quite a small neighborhood of practically any point in this weight space, you can find some local minima, and this local minima will bring more or less the same value for the loss function. So even if you go to if you converge to some local minima, it is not a problem because most of these local minima bring the same value of loss function. Some of them can be better generalizing than others, but still these functions are so wildly non-convex that it is not a problem. So, and it is astonishing how Hinton saw it in basically 40 years ago, because he's not talking about convex functions with billions of parameters. He's talking about functions maybe 1,000 parameters, and I'm not sure its phenomena happened there, but still it is. This paper is a gem, undoubtedly.
Well, there's something to know that the local minima are not singular here, right? You have global minimas are not singular. You
Yeah.
have multiple global minimas. Because if you have one global minima, you just take any layer, choose any two neurons in the layer, swap their positions, that's another global minima,
Yeah.
right? So you have many, many global minimas, or you could have, depending on the activation, you could even have like infinite non-countable number of global minimas, which is more common in the networks that we use today. So, I mean, he's not really touching on that here, but
Yeah.
I think he has spoken about that. So something he knew, maybe, he ran out of space in that paper.
Yeah.
And I would add that there's, and Mike, you mentioned generalization, but he didn't talk about it at all. The whole framework is just like what we call training today. There's there's pairs of data with outcome, and we minimize the error. So that's the learning part. That's it. No discussions of how it generalizes to things that it didn't see or whatever.
Are we going to talk about the figure 5? Because he's going to look at some sort of a recurrent network. I didn't go too deep
So
into
explain
it.
it. I didn't look into it. If you did and you have insight, explain to the audience what do we see and what are your
Yes.
thoughts?
So you can look at the left, that's the actual network. So you're seeing a network that is running through time, and there are connections between the elements that are being propagated through time. And on the right, you can see the unrolled version of the network. So you can see the first three nodes. The input of the first and the last one are connected to the middle one, and the middle one is connected to the extreme ones. And then it's running through time. So
time is going down or going up?
time is going up here.
Up. Okay, cool.
And I mean, doesn't really look like a complete explanation to me, because I'm not sure what are memories and what are outputs. I think it's not a recurrent network in the sense we're talking about. It's just a network that's being run several times. It's kind of similar to there's a concept of an infinite depth network that he will come up with later. And I think that more alludes more to that than what we think of recurrent network today, because I don't see where the inputs come in at different times here. But nonetheless, is showing that you can have multiple steps and you can differentiate through those steps. So this unrolling process is how we train recurrent or even transformer networks today.
Yeah, interesting.
I would like to add that this is 86, and back in the day, as far as I can tell, from my knowledge, it did spark a lot of interest in this area until they hit the first winter, right? What, like the 90s?
We're probably going to talk about the paper that brought it on, right? Because there's going to be a paper that says you never need more than 2 layers, and everyone was stuck on 2-layer neural
Yeah.
networks.
We have to do this paper. No
Yeah.
chance of not doing it.
Yeah, that's in the future. And we can finish by looking at, as we said, first let's wrap up with his summary. He says the learning procedure in its current form is not a plausible model of learning brains. Okay. However, applying the procedure to various tasks shows that interesting internal presentation can be constructed by gradient descent in weight space. And this suggests that it is worth looking for more biologically plausible ways of doing gradient descent in neural networks. And they cite 4 papers, and as we said, probably they didn't have a lot of space. But let's look at, okay, we don't see other papers, how many they have cited. Let's see here, go up. No, look, another paper above that was published in the same letter cited 27 other papers. So the claim that they didn't have space for like 20 citations or something is probably not true. They chose probably to write more at the expense of less citations.
Yeah.
And this triggered Schmidhuber, I guess. And because he will probably cover some of his papers. They came more like in the early 90s. And because he's a little bit younger also than Hinton. But up until today, I guess they don't like each other. Yeah, that's how I'm gonna finish the episode. Any takeaways from your side?
I think this paper is quite revolutionary. I think this paper alone, I'm not sure it can justify the Nobel Prize, but this is a very short paper with so many new and revolutionary ideas. It is so widely used today. So for me, it is 90% of the Nobel Prize. So before I started to read this paper, I know that it's a seminal paper, but you have tons of seminal papers, very important one. But this is one is special because it laid foundations for so many things we are using today. To just cool, very cool, and I think personal note, I think he deserves a Nobel Prize.
Interesting.
I think he deserves a lot of prizes, and he did get a lot of them. So yeah, I actually looked at the paper and feared, you know what? I'm curious, like, what would we look at today? And obviously, Hinton would look at today as well. And many of those appear in his later works. And he didn't look at here. And what did he look at here? So, like, which of the concepts do I feel were already predicted in the first paper? So Daniel touched the most important one, I think, which is generalization, that he doesn't talk about here, and he always discusses that. Like when I was learning his work, he would always discuss that. So that's one thing that surprised me. Another thing that he very lightly touches on is the optimization surface that and the properties you need for that. He says that you need bounded derivatives, and then he talks about the skip connect, not skip, sorry, having more connections prevent the problem of having bad local minima, which is very nice. He doesn't like touch saddle points at all, which we now believe are the problem. He doesn't touch convexity at all, which, this is non-convex, right? That's where the issue comes from. But convexity is not like you must be perfectly convex. There are other properties. There's like something which is can be close to convex but isn't really fully convex. So he doesn't really touch on that at all. Different loss functions. He's just saying that's the loss function. Deal with it. And it's like not conducive to classification at all. And classification problems did exist at the time. So like he clearly had one mind in that regard. But obviously that's an easy generalization, right? You just replace the mean square error with some other type of differentiable error. But he wasn't even in terms of regression, right? He was looking at mean square error, which, as Daniel said, is a Gaussian maximum likelihood problem, but he's not looking, for example, at absolute error, which is Laplacian distribution in the maximum likelihood sense. He does talk about recurrent networks, doesn't allude to convolutional neural networks or to choosing the connection between layers. But he's not touching on that. He's not touching on regularizations, which he talks a lot about, like in the last decade.
For that, you need generalization in your mind in order to introduce it.
Fair enough, right? He didn't discuss generalization at all. It was like, we're able to learn. I don't care if it generalizes. That feels like the point is here. Mentions skip connections, but doesn't actually use them. Well, it was used, I think, in 2015 by he et al. So to skip connections to make the networks closer to a convex loss surface. He doesn't talk about the activations being smooth. Actually, he does use a smooth activation, but he doesn't discuss other activations at all or like their structure, because you could have an activation function which is pretty bad, hard to learn with, right? Which would like be like a sigmoid from -1 to 0, then another sigmoid from 0 to 1. And if they're slightly spaced apart, so you would have you will get stuck on 0 because you have a gradient which is 0 very close to that. And he's not talking about that. He's just saying, I'm using sigmoid, but you can use whatever. It's nice that he talks about the initialization. We have some variants of that, but it's not too important how you initialize. And he does mention second order optimization, so Hessian-based optimization, but he's not saying anything about gradient-free optimization, like how much better is that than gradient-free optimization. So that was my checklist. Sorry if I bore you. Happy if you found that interesting. Tell me in the comments which one was it, so I'll learn.
You'll learn without generalization.
I have only one comment.
Yes.
I have only one comment in his defense. It is 4-page paper, so it can't it can include all the stuff you mentioned. Okay, even theoretically,
I have another point in his defense. That's like the first paper. Like even without thinking of all of that, that's like seminal and amazing that he could do that. You don't have to predict everything forward. I'm just saying now, looking back, which concepts would I look at, right? But what would I expect? But I don't think, like, he's one of humanity's greatest geniuses, and he couldn't come up with that. So the only thing I can derive from that is if I miss something like that, I should feel less bad about myself.
And I would like to add
Yeah,
something. So first,
exactly.
thank you, Liron. And I think today we know Hinton. Every person knows his name, but nobody knows the other two co-authors, Rumelhard and Williams, in my opinion, because of his perseverance, right? He continued throughout the winters that are coming, the AI winters, to do the research and actually address all the points that you, or try not to address all the points you mentioned, and pushing it forward. And I guess the other two moved on in my probably, otherwise we would have known them. So that's my also takeaway.
Well, I mean, it could also be for at least one of them that he was like in a later stage of his career, and when
That's true. The
deep
other
learning
two
started.
passed away, one in 2011 and one actually last year.
Okay, so or retired, right? They don't have
Yeah,
to die. They can
that's
just be,
true.
playing with their families.
Oh, shame on them. No, just
Yes.
kidding. You should all play with your family. That's super relevant. And on that note, I need to go to be with my family. So thank you, Mike. Thank you, Liron. Thanks to the listeners.
And thank
And
you,
we're gonna
Daniel.
meet you. Yeah. Thanks to myself.
Thank you.
And we're gonna see you next time.
Bye.